Hi everyone. I thought I'll spend two lectures discussing the solution of one of the questions I had posted on LinkedIn. Again, I think I posted this question a while ago. It's a question based on CMOS operational amplifiers. So we will first try to analyze this conventionally. So which is a very easy thing to do. It's just that the circuit looks very complex, but if you just break it down to its fundamental or the building blocks of the circuit, which is just if you see the circuit, there are only three blocks which are unique. I mean, these two look exactly the same. So you just have to figure out what is this block doing, and this block, what is it doing, and then the input circuit. So there are only three unique circuits in this. So if you're able to analyze these three circuits separately, then we can just combine and figure out the output voltage in terms of the input voltage. Now, there are some small interesting ideas which I wanted to test in this question. So which is conditional stability. So when you have multipliers, or I'll talk about it probably in the next lecture. In this lecture, mainly we will do a linear analysis and solve this problem. Okay. So in the next lecture, I'll talk about this case of conditional stability, which will happen when I say the conditional stability means that the negative feedback loops are stable under certain conditions. Okay, so which might happen when you have some nonlinear functions that we are going to see in this lecture. So now we'll go ahead and analyze the circuit. So again, I'll start with some very simple examples, equivalent circuits, and then try to give you some intuition and arrive at the final solution. So first, this problem is something that I've discussed long time back on the lecture series on operational amplifiers, basic opamp circuits. So I said that there is one very interesting property which we can, very interesting property of negative feedback amplifiers is the ability to invert mathematical functions. Okay, so of course, when I say ability to invert, those functions have to be, invertible. So that's the condition needed. Otherwise, we can still invert them, but answers may not be accurate. Okay, the rules for inversion should be that the function should be continuous in the region of interest. Then we should be able to invert those functions. So this is a simple negative feedback system. This is an ideal op-amp with an infinite gain. So I said whenever there is an infinite gain, then the error of the amplifier in the steady state, if the output is finite, then the error has to be zero, which means these two terminals will be equal in voltage in the steady state. So if V0 is the voltage that is fed to this nonlinear function, the output Vf is going to be f of V0. And the negative feedback will force these two nodes to be equal. Therefore, you'll end up getting Vi equals f of V0, or V0 is f inverse of Vi. So I can invert functions using this. So to take an example, let's assume where f of x happens to be x squared. It's a squaring function. Then your output V0 will be root of Vi, right? So the feedback voltage will be V0 square. So these two terms will be equalized by feedback. So your V0 will simply become equal to root of Vi. Okay, which is the third part of the circuit. Okay, if you look at this circuit here, the last part of the circuit is essentially a square root. It just computes square root of the input voltage. Now we will look at the similar properties of having a function, some kind of a nonlinear function in feedback, and see what it does. So here I have used a multiplier in feedback. So I have an output voltage V0 and I'm multiplying it by another voltage M of t, and that is being fed back at the input. Again, negative feedback prevails. This is right now we are not worried about whether we have negative feedback under all conditions or not. Let's assume that V0 is positive and M of t is also positive. Okay, mainly M of t is positive. M of t is positive for all time. So I'm simply multiplying V0 with M of t. Then I have a negative feedback loop here. Okay, so since I'm multiplying it by M of t, so what I'll get, the feedback voltage here, Vf, is going to be M of t times V0. Now these two nodes will be equalized by feedback in the steady state. So equate those two, you end up getting V0 as Vi of t by M of t. So arrived at a voltage divider. Okay, when I say voltage divider, I mean it can divide two voltage quantities. Similarly, if I put a division circuit in the feedback, let's assume you have a block which can take two inputs. So in this case, V0 and M of t, and it outputs an voltage, say Vf, which is given by V0 by M of t. So it's dividing two voltages. So let's say we have some circuit which can do that. Then if I put that in negative feedback, then this negative feedback will ensure that these two node voltages are equal. V0 equals Vf. So you'll end up getting V0 as Vi into M of t. So if I have multiplication in the feedback path, I get division in the closed loop transfer function. Okay. And if I have division in the feedback path, I end up getting multiplication in the overall forward transfer function. So I'll combine these two circuits, what I've discussed, the multiplier and divider, and build a circuit like this. So in the feedback path, I'm going to add a circuit like this. Okay. So this circuit, we just saw that if I apply V0 here and the other, I'm multiplying it with Vi itself in the negative feedback path, this node voltage, let's call that Vf of t. There is multiplication in the feedback path, so therefore the voltage for, I'm just looking at this part of the circuit alone, this voltage Vf is going to be V0 by Vi. Okay, we just analyzed it a few moments ago. The circuit shown in this circle region will simply act like a voltage divider. And this whole circuit is in negative feedback again. So if you see quickly, if I traverse in this loop, there is a negative feedback loop. Similarly, if I traverse in this loop, this is again a negative feedback loop. Okay, assume that if your V0 increases, output will also increase. So therefore there is that is fed back to this term, so the output will decrease. So therefore there is a 180-degree phase shift. Okay, so it's a negatively fed back circuit. So first I've realized a divider and then put that divider in the feedback path. Once I put the divider in the feedback path, I end up getting a multiplier. So what happens is these two nodes are now equalized by feedback. So Vi equals V0, so which means V0 by Vi equals Vi. So you end up getting V0 as Vi square. So I have realized a voltage squarer circuit using a multiplier, just one multiplier. I mean, I could have directly just, connected two signals to the multiplier this way and I would have gotten Vi square. I just wanted to test the understanding. So I just did this, try to slightly complicate it. But once you understand what's happening in the circuit, it's very simple to see that. The feedback path does a voltage division. So from here to here, it's just this part. If you just, so this part, if you just replace it with a voltage division circuit, it reduces to something like this. Okay, I've just divided, instead of M of t, I've fed Vi of t itself. So V0 by Vi equals Vi, so you end up getting V0 equals Vi square. So V0 by M of t, in place of M of t, you have Vi. So you end up getting V0 equals Vi square. So it's a squarer circuit. So now we have analyzed the second block as well. So with this knowledge, we'll see what is the output voltage. Now before I analyze this, the first half, let's assume this node voltage as V1 and this node voltage as V2. Okay, so now if you see, there are two halves of the circuit. So to one node, I'm applying Vi itself. So V1 is Vi. V2 is some transfer function, is some version of Vi which undergoes some transformation. So we'll not worry about that. Let's simply call the node voltage as V2 itself and V1 as this node voltage. So we just analyzed this. So again, one other point which I forgot to mention, in the question that I post on LinkedIn, I made a small mistake in the arrow mark. Okay, so this is what I've shown in this figure. The arrow mark is proper, but in the figure that I had given in the where I posted, it looks like the arrow mark was given here. That's wrong. Okay, so it's a negatively fed back signal. So your output gets multiplied by Vi and it is fed back. So this is the direction of the signal path. Okay, so opamps output goes to the input of the multiplier, which then goes to the negative feedback negative terminal or the inverting terminal of this op-amp. So in the question that I had posed, I just gave like this. So that doesn't make sense. I mean, you don't feed, there is no input here. So yeah. So I think some of you pointed that. So yeah, I made that change here. So I didn't look at it when I was just drawing it. So I probably made some small mistake. Yeah, I'm sorry for that. So here, if this is V1 here, we just analyze this circuit. The output of this circuit is going to be, so see here, we have, let's call this node voltage as some Vx and this node voltage as Vy. What are we doing here is that Vx times Vi, so this node voltage is going to be Vx divided by Vi. So this circuit is a divider circuit. It's a op-amp with a multiplier in feedback. So you're going to get a voltage divider. We just analyze the circuit. So let me not do that again. So you can just rewind back and see how the circuit is analyzed. So if I give Vi here, V1 here, the output at this node is going to be V1 square. Similarly, if I give V2 here, the output here is going to be V2 square. And that is summed using two resistors. So it's an averaging circuit, right? So if I have two resistors, the voltage at the center is going to be the average of the two voltages. So V1 square plus V2 square by 2. Now this circuit is a square root circuit. So if V0 is the output voltage here, V0 square is the voltage here. So equalize these two node voltage. Negative feedback will ensure that both these node voltages, the inverting and the non-inverting terminals, will follow each other. So you'll end up getting V0 as root of V1 square plus V2 square by 2. So now the question is, what is V1 and V2 in terms of Vi? So that's the first part of the circuit. So the first block, we will just analyze that. So I've shown the first block here. Again, this is also an op-amp and another op-amp in negative feedback. So you can just quickly see this is a negatively fed back circuit. You just traverse the loop here. You see that it's a negatively fed back circuit. Okay. So from the output terminal, if you increase the output terminal, this node will increase and this output will increase. And since it is fed to the negative terminal, this output again decreases. So it has it has an effect of trying to oppose any change. So therefore we said there is a 180-degree phase shift in the loop. So therefore we said such loops are negative feedback loops. So now we will analyze what is the output voltage for the circuit. So this output voltage is V2, which is what we need to figure out in terms of Vi. So if you look at the circuit, Vi also has another path to this node. So there is a resistor R which is connecting here. So that's what I've shown here. So Vi here, V1 here comes through a resistor to 2C, to this node. So there is another path, which is what I've shown here as well. Okay, so this is output voltage V2 and the input voltage Vi is also in the feedback path. So to solve this problem, again, it's a straightforward analysis problem. So you just have to look at see what the circuit is doing. So we can apply superposition to figure out what this node voltage at this point is. So the circuit reduces to something like this. So let's assume V2 is 0. So then I'll have from Vi to this node voltage. So let's call this V int, or the intermediate node voltage. So it's going to look like this. R, 2C and R will come in parallel because this node is now ground. We have grounded V2. So this is a simple RC circuit. We have already showed how to analyze circuits. So the DC transfer function is half, and this circuit doesn't have any zeros. The zero is at infinite frequency. That's the point where the capacitor acts like a short. So that's the infinite frequency. So you have 1 by 2 and no zeros. Since there is only one capacitor, you'll have at max one pole, and the pole frequency is 1 by RC. You can easily see that 2C into R by 2 is the effective equivalent resistance. So you get 1 by RC. So the transfer function, this is a low pass function. It will be half into 1 plus 1 by SRC, 1 by 1 plus SRC. Similarly, I can short Vi and assume V2 is present. So then I'll end up getting the same transfer function. The circuit is symmetric for Vi and V2. So you'll end up getting the same transfer function. So what you'll get here eventually, so this, I've called this node as V int or the intermediate node voltage, V1, Vi plus V2 by 2 times 1 by 1 plus SRC. Now, what is this circuit doing here? This circuit is simply a voltage amplifier. So it's a negative feedback circuit. It's a non-inverting amplifier. It gives you a gain of 1 plus R2 by R1. So this is R2 and this is R1. So that's simply a gain of 2. So then if I multiply it by a gain of 2, so then this goes away. So at the output of this amplifier, which is the feedback voltage, the feedback voltage is simply Vi plus V1 plus Vi plus V2. So let's call this as the feedback voltage is Vi plus V2 by 1 plus SRC. So, and since there is negative feedback, the negative feedback will force Vi equal to Vf. So therefore, you will have Vi plus V2 by SRC equal to Vi. Now, from this, you can directly get V2 as SRC times Vi. It's just a differentiator circuit. Okay, it's a very simple differentiator circuit. So I've just showed it and I've realized it using negative feedback. It's a differentiator without any, it's a non-inverting differentiator. So in time domain, V2 is RC to dVi by dt and V1 is Vi of t itself. So you know V1, you know V2. So the output voltage is simply V1 square plus V2 square by 2. So what you have is an expression that looks like this. 1 by root 2 into root of Vi square t plus tau square into Vi square of t. This is the mathematical function this circuit realizes. But now we are giving an input Vi of t which is equal to sine of t, sine omega naught t. Okay. Now what happens when I feed this input? I'll talk about it in the next lecture. Right now, if you assume your input voltage is always greater than 0, this circuit works perfectly fine. Okay, you will get the desired outputs. And why is that? The mathematics behind that, I'll discuss the next lecture. Okay, thank you.